Hey guys, I'm Zach and this is Sid, and today we're going to be giving you a TED Talk about solar and long-wave radiation. And just a quick note, Chris Lee is our cameraman.
Now, before we talk about solar and long-wave radiation, we need to first address the atmospheric system. So, our atmosphere is made up of several biogeochemical cycles. First, nitrogen, then carbon, hydrologic, or the water cycle, sulfur, phosphorus, and oxygen. And solar and long-wave radiation impact these cycles. As we impact the solar and long-wave radiation, that actually changes and impacts our atmosphere even more. And there may be too much nitrogen or too much carbon or too little water, and that might be a problem for us. And it impacts our organisms on a day-to-day basis. So the first type of radiation that we're going to talk about is solar radiation, and that originates from the sun. And it can come in either infrared, visible, or ultraviolet. And they're all typically short wavelengths, meaning that they're high frequency and therefore high energy, which really impacts our biogeochemical cycles and can cause a lot of problems for living organisms on Earth. And there are two different chemicals that that are in our atmosphere that impact whether solar radiation penetrates our atmosphere and actually hits the ground. And these two are HCl, hydrochloric acid, and HBr. And these two kind of determine whether they actually pass through, the solar radiation actually passes through, or whether it actually deflects off the atmosphere. And on the occasion when solar radiation actually does pass through in the atmosphere, depending on the albedo, which will be mentioned later, they will actually be reflected off the ground and trapped in our atmosphere.
So now we're going to talk a little bit about the relationship between solar incoming energy and outgoing long-wave radiation, which we've abbreviated here as OLR. So the first thing that I'd like to mention is net radiation. So net radiation is the difference between absorbed solar energy, that is solar energy that has entered the atmosphere and come in contact with Earth and has been absorbed by the Earth. So net radiation is that minus the outgoing long-wave radiation. And outgoing long-wave radiation is the energy that hits the Earth and is reflected back into the atmosphere. So net radiation is important because it's one of the variables that you can look at and scientists can look at to see what different types of energy are being put back to the atmosphere. So another interesting point is that latitudinal and longitudinal positions have very similar albedos and net radiations. So for example, I'm going to talk about the Amazon forest and the Sahara Desert. Although these seem like two very different places, they have one thing that is very similar. The Sahara Desert is 20 degrees in latitude north of the equator, and the Amazon forest is 20 degrees in latitude south of the equator. And although those may seem fairly unrelated, they have very similar albedos and very similar net radiations. Their albedos are very similar because both of them absorb a lot of energy, and their net radiations are because of that very similar absorption. However, their outgoing long-wave radiations are very different because the Sahara Desert is very hot, and that means that it emits a lot of energy and a lot of radiation, whereas the Amazon forest is very dense, and therefore it holds and stores a lot more of that energy instead of reflecting it back into the atmosphere. And then the final relationship between solar and long-wave radiation is the relationship between energy and temperature, which we will talk about in the next slide.
So in the previous slide we introduced long-wave radiation. I'm going to explain that in greater detail here, and basically what it is it's solar radiation coming in through the Earth, and it can do, as we said, one of two things. It can either be absorbed by the Earth, or it can be reflected off. And the radiation that is reflected off is what is known as long-wave radiation, and it is typically infrared and low energy, meaning it's high wavelength and low frequency. And it's directly related to temperature, and I have a little story I want to tell you that kind of explains this phenomena. So basically what it is on a cool summer's night, when you face the campfire and your face feels nice and warm, your hands get all nice and toasty, but your back is very cold because it's a cool summer's night, right? But when you want to heat up that back, warm it up, turn around, you feel nice on your behind, but your face feels cool. That is exactly what happens to the Earth when it revolves around its axis.
Alright, so now I'm going to finally explain the concept of albedo. So, to show you this, we have a picture of two different biomes. One is a grassy forested biome, and the other is an icy glacier biome. So let's first look at the grassy biome. So what you can see is that 70% of the incoming solar radiation is being absorbed by the grass and the ground cover, while 30% is being reflected back into the atmosphere. This is because grass and forested areas have a much lower albedo than icy glacier biomes and clouds and other things that are of that color. So when this is reflected, that means that about 30% of the solar radiation is being reflected back into the atmosphere. Now let's look at the icy biome. You can see that 85 to 90% of the incoming solar radiation here is being reflected back into the atmosphere, and that's much more than the grassy area because ice has a much higher albedo than grass and forested areas do. And this is all due to their color. Because ice is white, it reflects a lot more radiation and light, whereas grass is a much darker color, and that causes it to absorb a lot more of that energy. And an interesting fact is that when ice absorbs the 10 to 15% of solar radiation that hits it, this creates what's called a positive feedback loop. So what happens here is that the small amount that's absorbed causes the ice to get warmer and melt into water. When the ice melts, it becomes the water, and water has a much lower albedo than ice does. So water absorbs more solar radiation than ice does. So that means that when the water absorbs more radiation and it comes in contact with the ice, it creates a positive feedback loop by causing more and more of the ice to melt. So as more ice melts and as more water and ice absorb solar radiation, more ice melts. So the last aspect of solar radiation that we'd like to talk about today is the different amounts of incoming and outgoing solar radiation throughout the day. So as you can see, incoming radiation is pretty steady from sunrise at about 6 a.m. to sunset at about 6 p.m. And the blue line here represents the amount of outgoing radiation, and the red line here represents the temperature during those times. So as you can see, the amount of outgoing solar radiation here is pretty steady because it's dark and there's very little incoming solar radiation that can be bounced back into the atmosphere and become outgoing long-wave radiation. So that's steady, but then once incoming radiation begins to hit the Earth, there's a steady increase in the amount of outgoing radiation because more of that solar radiation, that incoming radiation that's hitting the Earth, is being bounced back and being turned into long-wave infrared radiation. And also, as you can see, the temperature is declining because from the previous day it starts to get really hot, and then it finally starts to decline once the amount of incoming radiation starts to decrease. So as you can see here, when the incoming radiation starts to hit the Earth, the temperature, very similarly to the amount of outgoing radiation, begins to increase at a very steady, very dramatic rate. And that's because incoming radiation is energy, and energy creates heat. So heat is increasing from the time incoming radiation starts hitting the Earth to the time, about the time that it stops hitting Earth. So when it gets dark at sunset, both outgoing radiation and temperature begin to decline because there's no incoming radiation to create either one of them.
Thank you for watching our presentation. I hope you enjoyed it and you learned a lot. Thank you.
See you later.